Okay, so this was our first example. This 49 meter per second, the velocity at which the acceleration is zero. So this is the equilibrium velocity. Okay, velocity once becomes 49 meter per second. Actually, theoretically, you never reach this velocity because uh, you get closer and closer to this velocity, but asymptotically you reach 49 even if you start with a higher velocity or lower velocity. uh, your limiting velocity is 49, but we call it equilibrium velocity. uh, and in practice, of course, you reach this velocity, and uh, after that the velocity doesn't change. So actually this is the principle, right? Parachutes works, right? Parachutes usually move at a constant and safe, of course, velocity. Here, of course, this is not very safe. 49 meters per second is very fast. Okay, if you hit the ground with that velocity, you cannot survive, I guess. Nevertheless, let's see another example. Oh, by the way, since this equilibrium point has the following property, that if you move a little bit above or below of this equilibrium, then a trajectory will take you back to the equilibrium, right? If you move a little bit high somehow, and then a trajectory will again take you back to the equilibrium. Or if you move a little bit down from the equilibrium, so if your velocity is somehow less than 49, then gravitational attraction will increase your velocity, and you will again reach the equilibrium velocity, which is 49 meters per second. That's why this equilibrium is called stable. Why stable? Because if you move above or below that equilibrium, you will get back to the equilibrium. Okay, that's why we call it a stable equilibrium. This equilibrium is called stable. Okay, because uh, if you move from the equilibrium, a trajectory takes you back to the equilibrium. So because if you move from the equilibrium, then a trajectory takes you back to the equilibrium. That's why we call it a stable equilibrium. Okay, stable equilibrium. Okay. Now let's see another example. So this is the example 2. Field mice and oval. So in this case, we study a biological problem. Uh, let's say we have a population of mice uh, in a field. So let's say this is the mouse at time t. Here t will be time in days. Okay. So let's describe what's going on. In the absence of predators, which becomes owls in our case, the mouse population increases at a rate proportional to the population. Uh, with, let's say, proportionality constant, say R. So we have this kind of equation. The population, mouse population, changes in time proportional to the uh, population. If you have, let's say, few, mouse, then of course their number will increase in small numbers. But if you have many and there are no predators, and we assume that food is plenty, so they don't have to fight with food, then their population will increase, of course, more rapidly because you have many mice. Uh, but usually things are not like this in nature. Now we assume that several owls lives in this field and they hunt 15 mouse per day. So they live on, live on mouse, so they eat mouses, and we assume that they kill 15 mouse per day. So okay, T is time in okay, months, not days, months, and say R is zero point 0.5. So this means what? Their rate at which the population increase is zero point 0.5. So we have then this equation. The population rate at which the population uh, changes is R times P. R is just zero point 0.5 minus, and every month how many mouse will die? Well, each day 15 mouse is killed by owls. So we have 30 days, and this is the equation we obtain. Of course, this is not, a very realistic equation. We ignore many quantities from, the system, in the system. For example, we don't care about the amount of food or other predators or some illnesses among the mouse population and so on. We ignore all these. So this is a very simple model. And our model gives us this differential equation 0.5 p minus 450. Okay. Now let's draw our uh, direction field again. Okay, so this is time again, and this is p. All right. If the population is 900, then so if p is 900, then uh, dp over dt is, okay, let me write here. If p is 900, then dp over dt is 0. So that's equilibrium. Velocity, so the rate at which the population is changing is 0, means population doesn't increase or decrease. Of course, every day 15 mice dies, but so every day 15 mouse also borns. That's why the population doesn't change. Okay. And if, let's say, this is 850, then dp dt is how much? 425 eder. Eksi 25. So minus 25. So this is something like this. Actually, it is much more than this, but if this is, let's say, 800, then dp over dt is minus 50. So even steeper. And if it is bigger than, let's say, 950 dp dt, so it will be 25. And if it is, let's say, 1000, then dp dt becomes 50. Yes, so here we have something like this, let's say. And then here it will be even steeper. You see from this direction field also that our model is not actually realistic. Yeah, if one of your friends warned me that I didn't start the recording, but actually I did. I am not recording using the Zoom platform. I am recording it direct to my computer using another program. But actually, it is good you warn me sometimes, because I forget to start recording, and then I have to take the record at some other time, spend another hour. So thank you for warning, but I started recording. Okay, thank you anyways. Now let's see our uh, you know curves, solution curves. Suppose the mouse population was larger than 900. What happens? So I have to draw a curve which is tangent to this direction. So it should go like this, right? Suppose it was like here, and it should go like this. Here it should go like this. Okay. These are the direction or solution curves. and here they go like this. So you see, if the mouse population somehow is less than 900, then the mouse population will decrease quite fast and they will all vanish, right? And according to this model again, if the mouse population is bigger than 900, this time the mouse population will increase very fast and it will go to infinity. Of course, both of these scenarios are not uh, possible in practice. The reason we obtain such strange results is that our model is not actually a complete model. We ignored many things, right? That's why we ended up something like this. uh, Nevertheless, the equilibrium point, so 900, not V, the population, which is 900, is the equilibrium, right? The rate of change at this point is zero, right? When P is zero. That's why this is an equilibrium, is the equilibrium, and it is this time unstable. Why is that? Because you see, if it is 900, it will stay 900. But if it drops a little bit, then the population will decrease to zero, right? It will not go back to 900 again. And if the population somehow increases and becomes more than 900, this time the population will increase over and over, and it will never go back to 900 again. So that's why this 900 is an equilibrium, but it is unstable. Okay. And as I said, this is an unrealistic uh, model. Okay. uh, we see that unlike the first example, this model is not realistic. Okay. Okay. Now, do you have any questions so far? What's a differential equation? And we have seen some examples, and we have explained what's a direction field and so on. But I didn't really solve an example, right? Now, this is what we are going to do. We will solve some equations analytically, solutions of some differential equations. Okay. Let's start with our first example. What was the example? Okay, yeah. It was this, right? dv dt is equal to 9.8 minus v over 5. Here v is a function of time. Okay, how can we solve this? Well, this is what we are going to do. You see, uh, dv over dt, sorry, divided by v minus 49 is equal to minus 1 over 5. So here I have what? I have derivative of v, and then we have v over 49. Here I have constant. Well, we see that the left hand side is nothing but derivative of what? This is just the derivative of, from calculus we know that this is just derivative of logarithm of v minus 49, right? Because when you take the derivative of this, you take the derivative of inside, which is dv over dt, divided by v minus 49. So I have a function whose time derivative is equal to minus 1 over 5. Then what can we say about this function? Well, then this function, if we integrate both sides, we get ln v minus 49 should be antiderivative of this gadget. So antiderivative, let me write it this way. And what is this? This is just minus t over 5 plus a constant. Okay. And from this, of course, we get what? I would like to obtain v. So to solve this equation for v, I have to take exponentials of both sides. So we get what? V minus 49 is equal to exponential of this, which is this. So I can write it this way: e to the power some constant times e to the power minus t over 5. And from this we get v minus 49. And if I drop this absolute value, then I get plus minus e to the power c and t over 5. Here, what was the c? C was an arbitrary constant, right? E to the power c is an arbitrary constant also, but it is not actually that arbitrary. Since it is the exponential, it is positive. So this is an arbitrary positive constant. It's not zero even. And here I have plus minus sign, so that this becomes what? This becomes now an arbitrary constant because it can be negative, but it cannot be actually zero, right? It cannot be actually zero because it is e to the power something. And from this we get 49. And then I have, so this plus minus e to the power c is just another constant. Let me actually c prime here, and c is just plus minus e to the power uh, c prime. Here c prime was an arbitrary constant. Arbitrary constant. Here this was a positive number. Now it becomes a non-zero number, and here it became a positive, an arbitrary constant, uh, and I have, of course, this gadget. From the algebraic manipulations, we see that this c cannot be zero, but in fact it will be zero. So here c is not C is a real number but not 0. However, actually C can be 0, right? However, C equals 0 gives Vt, which is 49, the equilibrium solution. So you may wonder, why we have something like this. Uh, this method we used gave us almost all the solutions, but not the equilibrium solution. Uh, this is because, when you start solving your equation, you make some actually assumptions. What's that assumption? Here you see, I divided this equation by v minus 49. And whenever you do this, you assume that velocity cannot be 0. That's why, you know, we obtain this solution, and this solution uh, avoids the equilibrium solution. Okay, so but in general, of course, C can be 0, and that's also a solution of the differential equation. Uh, the problem is that our method has some deficiency, and it excluded the equilibrium solution. It doesn't mean that the equilibrium solution is not a solution. It's a solution, but our method just didn't yield that solution because at some point, to make life simpler, we made some assumption, and that assumption has a cost. And what is the cost? It ignored this method ignored the equilibrium solution. Okay, but we know that C can be 0, and it's the equilibrium solution. So any constant here, any constant including 0, gives us a solution, right? Any choice of C gives us a solution. We will see later that we will see later that these are all the solutions. Okay, so far I don't have such an information. I obtained some solutions, but you never know that somebody else comes along and finds another solution which is not listed here, right? Here I say that any constant C gives me a solution, but how do I know that these are all the solutions? Maybe there is another solution, right? It is not clear from our discussion that these are all the solutions, but we will see later that actually this gives us the whole list of solutions. Okay. All right. Maybe I should give the other solution. Uh, well, the solution of the other example. In that case, our differential equation, this field mice and oval problem, it was this, right? And here we make a similar manipulation. T minus 900, and here I have 1 over 2. Okay, and we see again that this is nothing but, the left hand side is nothing but logarithm, derivative of the logarithm of t minus 900, right? Therefore, integrate both sides, I get ln p minus 900 is integral of 1 over 2 dt, which is just t over 2 plus a constant. Let me write it c prime. Here c prime is any constant. And from this, of course, by taking exponentials of both sides, we get this. And this is just e to the power c prime times e to the power t over 2. And if I drop the absolute value sign, I get this. And as above, I will let this thing be another constant. Okay. Here, c cannot be 0. It's a real number, but it cannot be 0 because it is e to the power something. But we know that so this is just zero. However, as above, c equals 0. Indeed, c equals 0 gives us the equilibrium solution. Constant solution, pt equals 900. Okay, so these are the solutions, including c equals 0. In fact, we will see that pt, which is 900 plus c to the power t over 2, and c is any real number, is the list of all solutions. Okay, we don't know at the moment why this is the list of all solutions, right? I applied some method and obtained some solutions, but how can we be sure that if, somebody else can find other solutions, right? At this moment we don't know, but we will see soon that actually this is the list of all solutions. Actually, for these examples, especially for the previous example, existence of other solutions could be something weird. Why is that? Suppose you are jumping from a plane using a parachute, and you hope that your velocity will decrease and reach a safe velocity, and you will land to the ground safely, and you hope that this is the differential equation governing your you know uh, uh, what fell, and you hope that these are all the solutions, and these solutions tells you that your velocity will reach an equilibrium, and which is a hopefully a reasonable velocity, so that you will land without any injuries. But if there are some other solutions not listed here, this means what? Your journey from the plane to the ground can be something totally different, and it is not listed here, so you don't know what will happen. Okay, that's why that would be something weird if there are some other solutions not listed here. Okay, so soon we will see so-called existence and uniqueness theorem, which will tell us that this is the list of all solutions. Okay, all solutions, and that will guarantee that when you jump from the plane, your velocity will uh, change in time according to this, you know, uh, law, and your velocity, limiting velocity, will be like this. Okay, so it is good to know this. Otherwise, you don't know what will happen. Okay. Uh, all right. So uh, classification of differential equations. Let's see. Classification of differential equations. Any questions so far? Now I'll talk about different kinds of differential equations and how we name them and so on. Okay. If a differential equation involves derivatives with a single variable, then it is called an ordinary differential equation, which we abbreviate by ODE. Okay, ordinary differential equation. Otherwise, so if we have derivatives with respect to more than one variable, okay, then it's called a partial differential equation, because if you have derivatives with respect to more than one derivative variable, you have partial derivatives. That's why equation will be called a partial differential equation. Otherwise, the equation is called a partial differential equation, which we abbreviate by PDE. Okay. All right. The order of uh, highest derivative term in the equation is called the order of the equation. For example, in the above equations, both of them, right, we had only first derivatives, and we had only derivatives with respect to the single variable, which is time, right? So this first example is an first order ordinary differential equation, right? This is the first order ordinary differential equation. Let me write it here. So this is the first order. Okay, let me write here. First order ordinary differential equation. Similarly, this thing is also a first order, right? Ordinary differential equation, because it involves derivatives with respect to a single variable, which is t, And the highest derivative term, the order of the highest derivative term is 1 because I have only dp over dt. I don't have any second or third order derivatives. Okay, now let's see more examples of differential equations. For example, let's see RLC circuit. So what's an RLC circuit? It's an electric circuit. Okay, so this is the potential, so some electric source, and then I have a resistance, and then I have a capacitance, and I have an inductor. Okay, so this is R, this is L, and this is C. Okay. Bu da olmadı. Şöyle biraz daha güzel çizeyim. Okay. All right. Now suppose the current is given by this function et, it, current at time t. This et, the potential difference applied to the circuit, potential difference applied to the circuit, and here we have a capacitance C, and let's say Qt is the charge in the capacitor C. Okay. Now let's see how these quantities are related. I have electric potential applied to the circuit. It can be a battery, or the electricity from a plug or some other source. I have current, electric current going through the circle. It's a function of time. Here t is the time as usual, and these are the circuit elements. Well, we know what this potential difference is the sum of the potential differences at the ends of this circuit elements. Here I have some potential difference. What is the potential difference? Well, this is a resistance. It resists to the current. And the potential difference at the end of a resistor is proportional to the current, right? Which goes through the resistor. And the proportion constant is called the, is called R. And the potential difference is just R times I. So if the current is high, then the potential difference is high. If the current is small, then the potential difference is small. What about the potential difference here? Potential difference here. Well, the potential difference at the ends of a capacitor is proportional to the charge. Okay, if the charge is big, then the potential difference is big. If it is small, it will be small, and it will be inverse proportional to the capacitor. So if capacity of the capacitor is small, then even small amounts of charge will uh, result in big potential difference. If the capacity is high, then even big charges will not cause big potential differences. So the potential difference here is how much it is given as Qt divided by the capacitance. Okay. And what about the inductor? The potential difference at the ends of the inductor. Inductor is like resistance, but it resists not to the current, but the change in the current. If the current is not changing, then you don't see this inductor. It will not cause any problem. But if the current increases or decreases, if it is changes, then this will uh, put resistance to the current. If the current increases suddenly, then uh, this inductor will uh, resist to the uh, current, change in the current. If this decrease, if the current decreases, then this inductor will try to increase the current. So it will do exactly what the uh, current is doing. If the current is trying to increase, then this will try to decrease it. If the current is getting decreased, then inductor will try to uh, increase the current. Okay, it will do exactly the opposite. Therefore, the potential difference here is proportional to L times the change in the current. So it is derivative. Okay. So what we see from this is the following. The total potential difference, of course, is the sum of these three potential differences. So it is R times the current plus Q times C 1 over C plus L times the I dt. Sorry. Okay. Of course, Q and I are different. Why is that? You see, Q is the amount of current, charge, and charge, of course, uh, depends on the current, right? Uh, Change in the charge is nothing but the current, because to decrease the charge, uh, you should have some current so that the electrons will move, right? And so we know this. Uh, IT is nothing but the instantaneous change in the charge. Okay. So this equation becomes then what? This equation becomes then, okay, let me write it this way. Uh, okay. If I write everything in Q, then di dt is, of course, the second derivative of Q with respect to t. So this equation becomes what? L times di dt, which is just the second derivative of q, plus r times I, which is the first derivative of q, plus 1 over c times qt, and that's equal to et. So this is a second order ordinary differential equation. Uh, second order, why second order? Because this is the highest order derivative term, and ordinary differential equation because all the derivatives are with respect to t, right? Second order ordinary differential equation. All right. In the next hour, I will try to explain this RLC circuit using a different model. Uh, Here you see an electric circuit, but we can actually use another model for this physical model, which results in the same differential equation. And I'll do that in the second hour. Let me stop the